Next, we have John Knapman. He is going to talk about interplanetary launches using a space elevator.
Okay, fine. So this is a presentation about technology, um, methods for interplanetary travel using the space elevator. I want to talk about methods of gaining speed and also controlling direction, which makes a big difference to how many launch windows you can get. I'll talk about the method published by Matthew Peat, which is very interesting. And then I'll talk about another method with rotating tethers called secondary tethers at the apex anchor at 100,000 kilometers from Earth. I'll go into the centrifugal and gyroscopic effects and some points about action and reaction. So first of all, let's look at the plane of the solar system. Remember, the Earth is tilted with respect to this plane. Most of the planets are more or less in this plane, apart from Pluto, a little bit out. And the space elevator, of course, rotates around the Earth in the equatorial plane, which is at a different angle, therefore. And so if we're not careful, and obviously we will be careful, a spacecraft just launched would go towards Mars, but it would miss it by a substantial amount. So there are certain windows where we can launch it easily, but if we have control over the direction of travel, then we have many more opportunities for launching. So Matthew Peat's method is, first of all, to use the centrifugal force on spacecraft once they get past the geosynchronous altitude, because at that point, the centrifugal force will pull them outwards, and it's possible for them to accelerate as fast as 10 kilometers per second. That means traveling along the tether at 10 kilometers per second, which is a lot faster than we're proposing lower down. So it does create forces, and that is sideways forces, and he proposes, in order to get direction control, to put a large ramp at the end which can deflect spacecraft. And you can rotate that ramp to deflect them in any direction. You can get, therefore, velocities that combine the velocity due to the Earth's rotation, 7.7, with this 10 kilometers per second. So you've got, depending on the direction you choose, velocities between 12 and 17 kilometers per second. And that gives you some impressive times of flight. Minimum time to Mars, just 60 days. The longest time would be 800 days, which you'd only use if you wanted to launch every day. Generally, with the planets, we assume you would pick your time, unless you want to go to mass production Jupiter, Saturn, Uranus, and Neptune as well. But these times are far lower than can be achieved today, where typically today you have to do a gravity assist maneuver around Venus, and it takes many years to get to the outer planets. So the benefits are there. Now let's talk about the technology, because an alternative approach at the apex anchor is to have secondary tethers that rotate about the primary tether. Excuse me. And that gives you the freedom to launch spacecraft in any direction on the celestial sphere. Remember, the celestial sphere is a bit like the Earth as a sphere, longitude and latitude. They have declension and right ascension, which are similar. So a system of tethers and reaction wheels will provide stability, but we have to look, and launch capability, but we have to look at the gyroscopic and other effects. So this is a picture of the arrangement. You see a wheel rotating about the tether with about the primary tether with secondary tethers attached to it. You see a reaction wheel with reaction tethers on it, which deal with the gyroscopic forces, and then a second system, the same, some distance down the tether, about 1,500 kilometers down the tether, rotating in the opposite direction in order to deal with the momentum and provide a reaction mass. The physics work out if you have such a system, and they rotate like this. So the reaction wheel and reaction tethers rotate much faster than the secondary tethers from which you launch space vehicles. And these secondary tethers are 10,000 kilometers long. And so the velocity at the end will also be 10 kilometers per second, but your spacecraft is only subject to very modest g-forces. With the other methods, you get quite large g-forces, but really the g-force with this system is just about the same as Earth gravity, about 10 meters per second per second. So the secondary tethers are made of single crystal graphene, just like the primary tether. They're 10,000 kilometers long. There you are. And the spacecraft will move along them under centrifugal force, but they can go at a gentle speed. 250 kilometers per hour is sufficient because they'll gather speed as they go, picking up the speed from the tether and the wheels. So that way they get a gentle ride to the tether's end, much as we envisaged for riding along the primary tether as well. So there's a small Coriolis force acting on the tether, which will provide some drag, and so you have to have electric motors in order to balance out the momentum. But again, you get the 10 kilometers per second at the end of these secondary tethers, which will augment the 7.7 kilometers per second you already have due to rotation about the Earth. So tremendous benefits, and it takes 20 hours to traverse the tether, and so you can do that in basically launching every day. You need electric motors, and the motors fixed to the drive wheel would require a power of 14 megawatts. But since you actually got to drive the other wheels as well in order to keep the system balanced and avoid excess speed, it needs an overall power of 56 megawatts, which is rather more, which is some factor times, about 5 or 6 times what we envisage for an individual climber lower down. Perfectly feasible and powered by solar panels. So let's look at the forces that come into play here. There's, in addition to the centrifugal force that pulls the tether because of its rotating about the primary tether, there's also a centrifugal force due to Earth's rotation. We're rotating about the Earth as well, and that pulls the tethers outwards in the manner indicated here. The reaction wheel and reaction tethers also experience that force, but it's very much less. Only 2 or 3 meters will be the result of the movement, whereas you get quite big movements with the main secondary tethers. The gyroscopic force acts differently. The gyroscopic force, because of the way the rotations interact, will pull one side away from the Earth and the other side towards the Earth. The mathematics are in a paper which will accompany this talk when it goes to the conference in Dubai later on. So the combination of these two is that one side is not actually moved very much, but the other side suffers a double movement due to both these gyroscopic and centrifugal forces. And as a result, you need something to counteract that. And so the reaction wheel with its reaction tethers is a solution to that, whereas the drive wheel and the secondary tethers rotate once every 105 minutes, 13.5 times a day. The reaction wheel counter-rotates at 7.5 revolutions per minute. Those tethers are 20 kilometers long, and that's sufficient to balance the gyroscopic effects. And also the reaction wheel will absorb some of the angular momentum from when we accelerate the secondary tethers and their drive wheel, or when we speed up a spacecraft going along it. But a second set of tethers is needed with its own drive wheel and reaction wheel to absorb that momentum. Otherwise, you'll be trying to push against the space elevator tether itself, which is not realistic. So the setup then is you have paired sets of tethers. So 3 secondary tethers and 3 reaction tethers rotating around the primary tether, and then another set the same 1,500 kilometers away to allow enough room for the displacement due to the gyroscopic and the centrifugal forces. The solar panel's further out, and the Earth is down to the right of my screen. Now, what's the mass of all this going to be? The total, as you can see there, comes to 1710, and there are calculations behind this. It's not just a finger in the air. The available budget at the apex anchor is 1900 tons, so we're within that 1900 tons. This uses most of that available budget in order to do the extremely valuable task of launching spacecraft all over the solar system at high volume. It's even possible to launch craft outside the solar system towards other stars. Clearly, though, that it's still a relatively slow journey. So how do we start it up then? The answer to starting it up is, first of all, you speed up the drive wheels and the reaction wheels at the same time, and then start paying out the tethers, paying out all the tethers equally and simultaneously. And if you work out your power budget and how much energy you need, it will take 58 days. So here's an illustration of how that works as you gradually extend over that period of 58 days to get the thing started, keeping the balance by running them all at once so that all the forces are dealt with at the same time, the action and reaction, as well as the centrifugal and gyroscopic forces. The system is naturally stable. There's some analysis, mathematical analysis of that as well, but there will be some oscillations when spacecraft are released. We can move counterweights along the tethers to reduce oscillations. We can partly retract and pay out tethers, but more detailed work is needed on that. I have not studied the oscillation modes. But to keep a balance, we need to use all 6 tethers in turn for launching spacecraft. They all have similar capabilities. Now, what happens if we want exact control of the launch angle? We've got these tethers coming round every 105 minutes, but it may be we want to launch in between one of those. And to do that, we can slow it down with 120 degrees between each secondary tether. So a 60-degree delay or a 60-degree advance allows us to cover all angles. And to do that, you can move masses along the other 2 tethers, or you can, in fact, use the motors as well. We have a sufficient power in order to perform that in the 56 megawatts available. So in conclusion, I say that using the space elevator, there's more than one way to send spacecraft to the planets. And they only need fuel and reaction mass for course correction and deceleration at the destination. No need for the time-consuming gravity assist maneuvers. And we can launch daily to any destination, although logically, unless you're launching high volumes, you would typically wait for the outer planets until you get to a convenient time of the year. That's my conclusion. I hope you find it exciting that there are multiple ways.
Thank you for that presentation, John. I think that you've given us a lot of food for thought there.